About 252 million years ago, life on Earth came closer to total collapse than at any other known moment in the planet's history. This was the Permian Triassic extinction event, often called the Great Dying. It marked the boundary between the Permian and Triassic periods, and also the end of the Paleozoic era and the beginning of the Mesozoic. When people think of mass extinction, they often picture the asteroid that ended the reign of the dinosaurs. But the Great Dying was far more destructive. Entire ecosystems disappeared, oceans turned hostile, forests collapsed, and food chains broke apart. By the time the crisis ended, Earth was a profoundly different world. The survivors inherited a damaged planet, and evolution had to rebuild from the wreckage. The scale of the extinction is difficult to grasp because it did not merely remove a few famous species. It erased whole branches of life. Scientists estimate that around 81% of marine species vanished, along with about 70% of land vertebrate species. Roughly 57% of biological families and 62% of genera disappeared. Even insects, which are usually extremely resilient during environmental crises, suffered their greatest known mass extinction. Coral reefs, shellfish communities, amphibians, reptiles, and countless ocean organisms were devastated. This was not a normal turnover of species. It was a biological bottleneck so severe that the history of life was redirected. Many groups that had dominated the Permian never recovered, while others only became important afterward because the old world had been cleared away. The extinction appears to have happened in pulses rather than as one simple instant. Evidence suggests there may have been 1 to 3 distinct phases, with the main marine extinction pulse occurring over roughly 60,000 to 100,000 years around 251.9 million years ago. In geological time, that is extremely fast. Rock layers preserve signs of sudden ecological stress, disappearing fossils, changes in carbon chemistry, and shifts in the kinds of sediments forming in ancient seas. There is still debate about whether the land extinction happened exactly at the same time as the marine collapse. Fossil records on land are often less continuous than marine records, so timing is harder to prove. But whether perfectly synchronized or slightly staggered, both realms suffered catastrophic losses. To understand why the Great Dying happened, scientists look for a trigger powerful enough to destabilize the entire Earth system. The leading explanation is not an asteroid impact, but volcanism on an almost unimaginable scale. In what is now Siberia, massive flood basalt eruptions created the Siberian traps. These eruptions were not like a single volcano erupting for a few days. They involved enormous volumes of lava spreading across vast regions, with volcanic activity continuing in episodes over a long period. As magma rose through the crust and lava poured out across the landscape, huge amounts of gases were released into the atmosphere. Those gases began changing the chemistry of the air and oceans, turning a volcanic event into a planetary crisis. Two gases were especially important: carbon dioxide and sulfur dioxide. Carbon dioxide traps heat, so releasing it in huge quantities can drive global warming. Sulfur dioxide can cause short-term cooling and acid rain, but it also adds chemical stress to ecosystems. During the extinction interval, atmospheric carbon dioxide may have risen from around 400 parts per million to about 2,500 parts per million. That is a massive change. Estimates suggest roughly 3,900 to 12,000 gigatons of carbon were added to the ocean atmosphere system. Such a carbon injection would not simply make the world a little warmer. It would alter rainfall patterns, ocean circulation, seawater chemistry, and the ability of organisms to build shells, breathe, reproduce, and survive. The oceans were among the first systems to become lethal. As carbon dioxide dissolved into seawater, it contributed to ocean acidification. Many marine organisms depend on stable chemistry to build shells or skeletons from calcium carbonate. Acidified water makes that harder, and in extreme conditions it can dissolve or weaken existing structures. At the same time, warming oceans hold less dissolved oxygen. If circulation slows and oxygen is not replenished, deep waters can become anoxic, meaning oxygen poor. In parts of the Permian Triassic Ocean, conditions may have become euxinic, not only starved of oxygen, but rich in poisonous hydrogen sulfide. For marine life, this was a double or triple assault: hotter water, acidic chemistry, and suffocating or toxic seas. On land, the crisis took a different but equally devastating form. Rising temperatures would have placed severe stress on animals, plants, and freshwater ecosystems. Heat changes everything: how much water evaporates, how often droughts occur, how vegetation grows, and how animals regulate their bodies. Forests likely declined in many regions, and when plants disappear, soils erode more easily. Rivers carry sediment into coastal seas, further disturbing marine habitats. Land vertebrates faced habitat loss, food shortages, and climate extremes. The Permian world had contained diverse reptile-like and amphibian-like animals, but many of them vanished. What survived was not necessarily what had been most dominant before. Survival often depended on tolerance, flexibility, and luck. The Siberian eruptions may also have triggered secondary disasters. As magma intruded into sedimentary basins rich in coal, oil, and organic material, it could have baked those deposits and released even more greenhouse gases. Burning or heating these carbon-rich layers may have added extra carbon dioxide and methane to the atmosphere. Methane is especially potent as a warming gas over shorter timescales. Some scientists have also proposed that methane clathrates, icy methane deposits trapped in seafloor sediments, could have destabilized as oceans warmed. If large amounts of methane escaped, warming would accelerate further. This kind of feedback loop is dangerous because the original trigger no longer acts alone. The planet begins amplifying the crisis through its own systems. Another proposed contributor involves microorganisms. Some research has suggested that novel methane-producing microbes may have flourished under the changed chemical conditions of the late Permian world. If volcanic activity supplied nutrients or minerals that helped these microbes expand, they could have produced additional methane. This idea remains part of a larger scientific discussion, but it illustrates an important point: mass extinctions are rarely caused by one isolated factor. A volcano does not simply erupt, kill life, and stop. Instead, volcanism can alter climate, which alters oceans, which alters microbial communities, which then alter atmospheric chemistry again. The Great Dying may have been a cascade, where each stressed system pushed the next system closer to failure. Climate instability may have also changed weather patterns. Some scientists have proposed that El Niño-like events became longer and more intense during this period. In the modern world, El Niño can shift rainfall, drought, heat, and storm patterns across continents and oceans. In a much warmer Permian, Triassic climate, stronger or more persistent climate oscillations could have made ecosystems less predictable. Species can sometimes survive gradual change if conditions remain within tolerable ranges, but repeated extremes are different. Heat waves, droughts, floods, low oxygen waters, and food shortages can prevent populations from recovering between shocks. Even if an organism survives one bad season, its offspring may not survive the next. Over time, repeated stress can collapse entire communities. There are also more controversial ideas. One proposed factor is an extraterrestrial impact connected to the Araguainha crater in what is now Brazil. Some researchers have suggested that an impact there could have produced earthquakes, released methane, or damaged the ozone layer, increasing exposure to solar radiation. However, unlike the dinosaur extinction, where a giant impact has overwhelming evidence, the Great Dying is not mainly explained by an asteroid. The strongest consensus centers on Siberian flood basalt volcanism and the environmental chain reactions that followed. Still, scientists study alternative contributors because Earth's worst extinction was complex. A secondary impact, regional methane release, or atmospheric damage might have worsened an already escalating catastrophe, even if it was not the primary cause. The aftermath of the Great Dying lasted far beyond the extinction pulse itself. Recovery was slow because ecosystems had not merely lost species, they had lost structure. Reefs had to rebuild, food webs had to reform, soils and forests had to stabilize, and surviving animals had to diversify into empty ecological roles. The Triassic world that followed was shaped by absence as much as by survival. Over millions of years, new groups expanded, eventually setting the stage for dinosaurs, marine reptiles, and modern-style ecosystems. But the Great Dying remains a warning written in stone: Earth's life support systems are connected. When carbon, climate, oceans, and biology are pushed hard enough at the same time, even a planet full of life can become dangerously fragile. If you found this helpful, please like this video and subscribe for more explainers.